Okay, we're going to do some similar examples as last time, just a little bit different story. This one says at 5 p.m., Audrey is 3940 feet directly above Mr. Leanza. So we got Mr. Leanza down here. I'll just put it Mr. Then we got Audrey up here, and the total distance is 3940. At the same time, Mr. Leanza starts walking in a straight line at a rate of 84 feet per minute. So Mr. Leanza is going this direction. It says, what is the rate in feet per minute that the distance between the two people is changing 5 minutes later? So 5 minutes later, Audrey's going to be here, and 5 minutes later, Mr. Leanza is going to be here. So the triangle that we see is actually the ending triangle at 5:05 p.m. So if we notice that it's 5 minutes, we say, okay, if Mr. Leanza walks for 5 minutes, how far did he go? So the rate would be 84 feet per minute, and it's for 5 minutes. So we're going to multiply by 5 minutes. So we can cancel the minutes, and our final answer is going to be 420 feet. So that'll be our x distance from here to here. You see our diagram, that's the x distance. It's 420 feet. X prime is the rate of change of x, so it's how fast Mr. Leanza is moving. So for this example, we're going to say 84 feet per minute. And we're going to choose positive because that side of the triangle is increasing. So the derivative should be positive. Now, if we choose this side to be y, this side is decreasing. So the derivative will have to be negative. The rate for Audrey is 500 feet per minute, but it's going to have to be negative. Again, if Audrey's traveling at 500 feet per minute for 5 minutes, we can cancel the minutes again, and we're going to get 2,500 feet. But the 2,500 feet is the distance from here all the way to here. So if this is 2,500, but the entire distance is 3,940, we need to subtract those, and we get 1,440. So this y distance is 1,440. Now, if we know the x and we know the y, we can find z because we have a right triangle. We can just do x squared plus y squared equals z squared. Okay, we can solve this by doing the square root on both sides. The square root of z squared is just going to be absolute value of z. We can get rid of the absolute value if we do plus or minus, and we can move the plus or minus over to the other side. Of course, the side of a triangle can't be negative, so we'll just use the positive one. Let's plug this in a calculator. Our answer is 1,500, so z is 1,500. Of course, we're trying to find the rate in feet per minute that the distance between them is changing at 5:05. So we're trying to find z prime. We have this equation that relates x, y, and z, so we can do the derivative, and that'll get us z prime. Remember, we're doing this kind of a derivative, d dt, and none of these are the letter t, so we're going to have to do the chain rule each time. Derivative of x squared is 2x, and then x prime. The derivative of y squared is 2y, and then y prime. The derivative of z squared is 2z, and then z prime. We are solving for z prime, so I can divide everything by 2z. My final answer is that z prime is equal to xx prime plus yy prime all over z. We can go ahead and plug in the values that we found. Okay, we can plug this in a graphing calculator. Okay, our final answer is that z prime is negative 456.48 feet per second. And I did not round that number, that's the exact value. If I was rounding it, I should round it to 3 decimals of accuracy. Okay, for this example, we have a 13-foot tall T-Rex. So my diagram has a 13 feet right here. And we have a 36-foot tall light pole. So the light pole is 36. I'm calling this distance here in green, I'm calling that x. It doesn't matter, you can call it x or y. And I'm calling the shadow y. It does say that the T-Rex is running at a rate of 66 feet per second. Now, because that part, which I'm calling x, is increasing, then that means the derivative will be positive. So we're going to say that's going to be a positive 66 feet per second. Okay, so I'm writing that right here. X prime is 66 feet per second, but it's positive. If the T-Rex was running towards the light pole, then x would be decreasing, and then that derivative would be negative. It says, how fast is the length of the shadow changing? So I'm using the red part, calling it y, and that's my length of the shadow. So how fast is the length of the shadow changing? Well, that's just going to be y prime. Since y is the shadow, y prime would be the rate of change of y. And so that would be how fast y is changing. We're going to use geometry to set up an equation that relates x and y. First, let's look at the small triangle. I'm going to say 13 over y. So I'm using the left side over the bottom. I'm going to do the same thing for the big one. So here's the big one. Then I want the left side over the bottom. Left side is 36, and the bottom is x plus y. We want to solve this equation for y. Let's cross multiply. 36y is equal to 13 times x plus y. Distribute the 13 and then subtract 13y from both sides. Last step, divide by 23 and we're done. And now I've found an equation that relates x and y. Remember, I'm looking for y prime, so I just need to do the derivative. Remember, I'm doing this kind of derivative, d dt. That's not a t and that's not a t, so I'm going to have to do the chain rule each time. The derivative of y is going to be dy dt. This is just a constant. The derivative of x is going to be dx dt. Put the constant in front of it. Remember, I was solving for y prime, so all I need to do is plug in dx dt and I'll be done. Let's plug this into our graphing calculator. Now, if this number reduced, my calculator would do it for me. You can see that that didn't happen. We just get 858 over 23. The units are feet per second. And that's how fast the length of the shadow is changing. Sometimes it asks how fast is the tip of the shadow changing. In that situation, you have to add the speed of the T-Rex. Because the T-Rex is traveling at 66 feet per second, you would just add 66 to that. We'll do that in the graphing calculator. So the length of the shadow is traveling at 858 over 23 feet per second, and the tip of the shadow is traveling at 2376 over 23 feet per second. All right, well, for this example, it says that wine is spilled from a barrel, but it's spreading in a circle. So we basically have this circle right here. It tells us the circumference is increasing at this rate. Remember, the circumference is kind of like the perimeter. Formula for circumference is right here. And if the circumference is increasing at this rate, that means that's the derivative of the circumference. So that's c prime. And we're going to go ahead and write that down, that c prime is equal to 27 feet per second. How fast is the area of the spill increasing? So it's not asking for the area. It's asking for the rate that the area is increasing. So that's going to be a prime. Remember, it's just a circle. So if you start with the area of the circle and you do the derivative, we're going to do d dt, and none of these are t's, so we're going to need the chain rule. But if we do the derivative of the area, we can get a prime. Let's go ahead and do that. The derivative of a is going to be dA dt. That's also a prime. The derivative of r squared is going to be 2r, and then r prime. So our final answer is a prime. All we have to do is figure out what is r and what is r prime. We were given c prime, not r prime, but we can use c prime. If we just start with c and we do the derivative, we're going to get c prime. And we know c prime is 27 feet per second, so we can trade that. So we can plug that in. We want to divide both sides by 2 pi, and then we'll be done. This will cancel. And now we know that r prime is 27 over 2 pi. So we can trade the r prime for 27 over 2 pi. We can bring down the 2 pi r. I'm just going to write this as a prime. Now you'll notice we still need to figure out what is the r. It is asking us to find a prime when the circumference is 86. So if the circumference is 86, I can plug in an 86 here, and I can solve for r just by dividing both sides by 2 pi, or maybe you notice that we have a 2 pi r, so I can trade the 2 pi r for 86. Now we can easily do 86 divided by 2. That's going to be 43. And it's actually okay to leave your answer like this. You don't have to multiply it out. But we do want to include the units. Remember, this is a prime, so it's the rate that the area is changing. So it's going to be an amount per time, but the amount is going to be an area. So area is always square units. This one is feet, so we're going to say square feet. And the time is seconds, so we're going to say per second. Now, if you want to write the top as a single number, we can type that in a calculator. We get 1161 over pi. And if you want to write it as a decimal, we're going to push green enter, and you get 369.557 square feet per second. And that's it. Okay, this is our last example. It says in the figure shown, the space shuttle is lifting off straight up. So the distance between the ground and the space shuttle is going to be y. And then it says 225 yards away, Bugs Bunny is watching. At the moment that the elevation angle is pi over 6 radians, the shuttle is rising at a rate of 326 feet per minute. At what rate in radians per minute is the angle of elevation changing at that moment? So theta is going to be your angle of elevation, but theta prime is going to be the rate that the angle of elevation is changing. And that's what it's asking for. It's asking for theta prime. So our final answer is going to be theta prime. So we'll write that right there. And we're going to start by creating an equation that contains theta. So with this right triangle, we can do tangent of theta is going to be opposite over adjacent. So tangent of theta is going to be y over 225 yards. Now you'll notice later on it has feet. So if it has yards and it also has feet, we kind of want to make everything the same units. I prefer to make everything feet. So if we have 225 yards, we know that 1 yard is the same thing as 3 feet. So that gives us 675 feet. And again, our final answer is going to be theta prime. So we want to do the derivative of this, and that should give us our theta prime. Okay, the derivative of tangent is going to be secant squared, but we're doing d dt, and this is not a t. So we're going to have to do the chain rule. We're going to have to do the derivative of theta with respect to time. That's also a theta prime, but you can write it as d theta dt if you want to. On the right side, we were able to plug in a 675 feet instead of just an x, because the bottom of this triangle is really an x, but the 225 yards is a constant amount. So if it's a constant amount, you can plug it in before you do the derivative. So that's going to make things easier. Instead of doing a quotient rule here, the bottom is just a constant. So really, I'm just doing the derivative of y. The derivative of y is just going to be dy dt. That's the same thing as y prime. And the constant, we just leave it in the front. Again, our final answer is going to be theta prime. So we want to get rid of the secant squared. I can rewrite secant squared as 1 over cosine squared. Remember, 1 over cosine is the same thing as secant. So I can trade the secant squared for 1 over cosine squared. Now if I multiply both sides by cosine squared, it's going to cancel the cosine squared on the left. So this cancels, and we're just left with d theta dt. Now we want to find d theta dt at the moment when the angle of elevation is pi over 6. So we can plug pi over 6 for theta. So that's the same thing as cosine of 30, which is root 3 over 2. After we square it, we get 3/4. And again, if you look at the triangle, this side of the triangle is y, and the rate that y changes is going to be y prime. So we can plug that in right here. That's just going to be the speed of the space shuttle. So at the moment that we're talking about, the rate of the space shuttle is going to be 326 feet per minute. So we can plug that in. Okay, it's helping us out with the units here. It says radians per minute. And we just want to plug all this stuff in a calculator and see what it tells us. Okay, it's giving us 163 out of 450. If you want to see the decimal, you push green enter. We're getting 0.362 radians per minute. Now, if this was a free response question on the AP test, I would just stop right here. There's no reason to make any more simplifications. Plus, it will take time and you might make a mistake. So just stop right there and move on to the next question.